Okay, today we finished up talking about induction, and just kind of a little bit of review of what we talked about yesterday. And then we are starting the process of the review for the final. And one of the things we can do for that is helping kids with some questions about the packet, the take-home final. And again, I am not going to do the questions from the take-home final on the board. That'd be really dumb, because you're getting graded on this and it counts as your final. But if you have questions about topics like, oh, the thing that they're talking about in number one, I'm not sure I remember how to do that stuff, I will be willing to cover that topic. So the first question I've been asked and the class agreed would be nice to talk about has to do with taking a function. Okay, the one in the packet is this. The function is e to the x minus 3, and they want us to sketch it, and they want us to find the domain of the inverse and the rule of the inverse. That basically just means what is the inverse. Okay, so when they say the rule of the inverse, that's just find the inverse. Do you remember how to find an inverse? All right. So let's talk about those concepts, the concept of the domain of the inverse and finding the inverse. I'm not going to do this one in particular. Okay. I'm going to do a log, which is very similar to an exponential. Well, let's just talk about exponentials and logs a little bit too. Okay, so here's some help for that first topic. Exponentials look like that in general. Okay, that's really general, but how big the base is how tight the turn is. If you had a base 10, like let's say this was y equals 10 to the x, then that would be a much tighter turn. It'd be like super steep, okay? So that's exponentials. Now, how about finding an inverse? What was that rule for finding an inverse? Let's say it was like that. That's a pretty simple one. Do you remember how to find an inverse again? It has to do with x's and y's, and what do you do with them? Switch them. Okay, so if I change it to x equals 2y over 3, I can't just be done. I got to now solve for x. No, I already solved for x, so solve for y. So then I'm going to divide or multiply both sides by 3. 3x equals 2y, and then I divide both sides by 2, and this kind of makes sense even that that's an inverse, right? Okay, but remember, you just switch x and y, and then you solve. That's how you find an inverse. So does that work for exponentials too, like e to the x? Sure. If you just had y equals e to the x, and you wanted to switch x and y, it'd be x equals e to the y, and then could you solve that for y? Yeah, you'd have to know how inverses, how to solve that, which involves what? Exponentials are kind of closely tied to what other thing? Logs. So let's just take a second and talk about logs versus inverses. Let's say you had this. What's that the same as an exponential? 2 to the y equals x. So you got to be able to rewrite things back and forth between exponentials and logs. So that first question is a very good question because it tests, do you know what an inverse is? And do you know how to rewrite things? Okay, so again, I'm not going to do the one they gave you. But let's say I had 5 to the x, and I asked you to do a inverse of it. What would be your first step? Switch x and y. X equals 5 to the y, and then how do I solve for y again? I do a rewrite as a log. So this would be log base what? 5 of x is equal to y. And there, I've got its inverse. Now, I'm not saying that's your answer. Of course, I did something different. All right, so that's how you do inverses. That's how you do logs. Oh, one more thing. Then they start talking about the domain of the inverse. Do you remember how since we switched x and y, that means the domain and range get switched? So if I have an equation that's like this, and then I say, oh, now I want its inverse. Well, if I knew its domain and range originally, I'd figure that out. Because when you get the inverse, if all I wanted was the inverse's domain and range, I wouldn't even have to find the inverse. I could just say, well, whatever the domain was, that's going to become the range. And whatever, 3 dots apparently, and whatever the range was, that's going to become the domain of the inverse. Remember that concept? All right. I think that covers everything you'd have to know to handle that question. And it's a little bit of logs, a little bit of inverses, a little bit of domain and range. How do you actually get domain and range again? The domain is all real numbers except x cannot be 0. I would typically write that as negative infinity to 0 works, then it doesn't work at 0, and then it starts working again after 0 to infinity. Sorry, that's a little scrunched there, but if there's a domain, you're saying to yourself what works, and you usually start with everything works except what? And the only thing that wouldn't crash this one would be x, would be 0. Okay, and then the range of it, I would sketch it, and once I had a sketch of it, and if you remember this one, it's the butterfly, and I'd look at try to figure out my range from that and go, oh yeah, the range will be everything works except, and again, I'd say to myself, okay, range goes this way, and it looks like the one thing that can't be is across here. Anyway, so figure out your range from a picture. We almost always do ones that you can sketch, because finding a range is really hard algebraically, but once you make a picture, that's one of my #1 tips in general for math, is like on the ACT test. If there's no picture, most ACT questions have a picture. So isn't that kind of a hint that maybe you should kind of make a picture or a chart or something? Maybe, you know, like make some sort of other way to display the information, and that oftentimes is how you solve the question. Same thing with your final in here. If there's no picture, make a picture. Like, what's the range? I could think this through and get the range, but a lot of you couldn't. But if I graphed it and said, what's the range, pretty much everybody could get it. This is a parabola that has a vertex at 4, 5. So now that I make that, I bet you almost everybody could get the range right. See what I mean? Pictures, way easier than anything else. So make a picture. All right. That was a good topic. So what else do you want to talk about? What else in the packet stumped your group and probably stumped other people? Yes. Everybody please look at number 10. Consider question 10. I know some of you haven't even looked at it yet, but to get your head around it for a minute and decide if that's something you'd like to talk about. That's called a piecewise function. Be honest, how many of you feel like if that question came up on the test that you'd be good with that? All right. How many of you feel like you could use some help on that? That's quite a few hands, so I will help with that. All right. I am not going to sketch this graph. I will make one similar. I'm not going to tell you the range, but again, after you get the picture, ranges aren't hard at all. Is it continuous? Okay, continuous is a different concept we should talk about. So if I have a graph and it goes like this, was that graph continuous? Yeah, it didn't have any weird spots in it. Okay. How about if I have a hole in the graph? That happens. Is it illegal? No. Is it have no domain and range? No, it's got domain and range. That's all. But it's not continuous because it doesn't. Here's the easy way. It's not a mathematical description, but if you'd have to lift your pencil up in the course of drawing the graph, if you can't do it in one continuous line, then that was not continuous. So that's not continuous. All right, so here's another one that would be not continuous. As I go from left to right, the graph goes like this, stops working, and then starts again, going like that. Do you get how that was not continuous? Okay. Can't do it all without lifting your pencil. Okay. Because it has an asymptote. Usually the things that cause things to not be continuous is if it has an asymptote or a hole in it. They're called discontinuities. All right, so that's the continuous part of it. How about this whole f of x is 3 things. F of x is just x. No, it's not. That wouldn't be. F of x could be x plus 4 if x is less than 0. It could be x squared if x is greater than 0 but less than 2. And it's 1 over x if x is greater than or equal to 2. All right, one thing we have that's a problem is that 0, right now, nobody owns 0. Think about that. These are 3 separate graphs. Just think of it as I got to graph this between up until 0. Okay, so this graph right here happens when x is less than 0, so in that little zone right there. This graph goes between 0 and 2. Okay, that's 2. Okay, and this graph will be graphed in that little zone. And lastly, this graph will be graphed in the third zone where x is bigger than 2. But I know who owns 2, but I can't tell who owns 0. Do you get how nobody therefore owns 0? And therefore this graph cannot possibly be continuous. You know what I'm saying? Because you're going to have to stop and not put anything at 0. You're going to have to have a hole at 0, or at least nobody owns that spot. All right. But if I change this just a little bit now it's possible this graph could stay continuous. Although, if I remember correctly, 1 over x is going to be one of those things that goes like this. And there's going to be a gap between this 2 and when this graph kicks in. Maybe, but maybe not. All right. So I'm not going to judge my continuousness until I have graphed it. All right. Now, I know you may not care that much about this question because you really care about the purple one. Okay, I get that. But here's my hint for how you do these kinds of problems. I don't want to belabor this one on the board, but do you get that each of these is a separate graph and you just make a little XY chart for it? I've told you before, the XY chart is your best friend in graphing. It'll graph anything. As long as you can find some points on it, you just can make enough points, you connect the dots, you got it. Okay, so make an XY chart for this one, make an XY chart for this one, make an XY chart for that one. That will keep you from having to memorize 8 million parent functions. Now, there are a few that you probably should know. Let's talk about that for a minute. Again, you have the choice. You don't have to listen to me, but you're not going to get that much instruction from me between now and when you take the final. So if I were you, I'd take notes instead of doing your packet, because you can do your packet at home. What parent functions should you know? How about this? Let's make a list of ones I would expect you to know coming in. X squared. You better know what that is. Absolute value of x. Better know what that is. 1 over x. Some of you aren't going to know what that is, but it's that guy. You need to make sure you include the asymptotes when you graph it. Okay, there are 12 parent functions. I won't expect you to know all of them yet, but that's 3 of them. How about this? Remember x cubed? If you don't, you should. And give me another one that I'm not thinking of right now. Square root, thank you. And it looks like this. One of them is just like too easy. You don't even think of it because it's too easy. And it's y equals x. That's one of the big 12. And I'm surprised at how many kids forget what it actually looks like. There you go. That's y equals x. Is there more? Oh, yes, there's more. But those are the big ones that I expect you to just know right off the top of your head. Then we get to the logs and exponents. I gave you one of these earlier. This is still considered a parent function, one you should know. E to the x. Generally looks like that. Again, if I needed exact points, do you get I would break out a XY chart? Do you remember that what E is? 2.7 approximately. E is about 2.7. 2.718 if you want to know exact. Well, it's not even exact. It's just a little more exact. Okay, and then how could I get points? Again, XY chart. Stick in 0, see what you get. What if I have an e to the 0? Well, that's equal to 1. That's why this graph always goes through 1. And then I could try sticking in e to the 1. Put in x is 1. E to the 1 is e, which is 2.718. So I go over 1 and up 2.718, etc. Okay, that's the e to the x function. And how about log of x. Now, if I just, not log base x, sorry, log x. And I should say log base 10 of x. Notice there's no 10 there, but you have to know that. But if they just say log, what base does it have? 10. All right. So here's log. And, nope, that's exponential. Sorry. Here's log. I've told you before, a dumb little way to remember this is it's like a tree blown over in the wind, because that's what a log is, right? If you have a log laying in your backyard that you sit on for your fire pit, we used to be a tree, and apparently it came down. Maybe it was blown over in the wind. Log looks like a tree blown over in the wind. All right, and that's base 10. How about if it was base E? Well, it's just a different base, so that means the turn is either tighter or looser. The bigger the base, the tighter the turn. Same with this kind. If this base had been bigger than 2.718, if this base had been 8, this would have turned a lot sharper. Okay? And if this base is an E instead of a 10, then it would turn a lot looser. Wouldn't turn so sharp. All right, so there's some parent functions that you ought to know off the top of your head. That's 8 of the 12. We haven't really talked about the basic logistic function or some of these other functions, so obviously we can't include that on your final. So. All right, I think I've covered that topic as well as I can without giving you answers. What else do you want to know? Anything else off the purple packet? Yes, sir. Everybody please turn and consider number 8. All right. Right away I see it's got a fraction in it. It's a fraction function. It's got a fraction in the equation anyway. So if it's like this, how am I going to solve that thing? My first advice to you has always been get rid of the fractions. Clear the fractions. It's one of the top 20 things. That says a lot. There's a lot of things in math. I only picked 20. And one of the top 20 was clear fractions. So how do you fix this? Well, multiply by the denominator. What if there's 2 denominators? Well, multiply by both of them at the same time. Does yours have 2 different denominators? Yeah, it does. So kind of similar to this. So if I wanted to clear this, I would multiply by 2 and 3 on all 3 parts. That's a really common mistake, is to forget to multiply it by all the parts. Then this 2 cancels this 2, this 3 cancels this 3, and then I'd have 3 plus 2 times 2 is 4a equals 6, and if you can't solve that, you aren't going to pass your final. All right, so once you clear the fractions, it actually becomes much simpler. All right, now they have a quadratic over there in the problem also. You're supposed to know how to solve quadratics? Oh, yes. Quadratics are the #1 most popular function for pre-calc teachers to use, because we figure you did a lot of quadratics previously. You should already be pretty familiar with them. And my favorite saying applies. What is it? You can factor it. You should. And so that's how you solve them, is by factoring it. And if you're solving it, you're trying to find the zeros, right? What are they? There's spots on the x-axis. They're x-intercepts. There's zeros. There's solutions. They're roots. They have 4 names. They must be important. So if they're the x-intercepts, they were y equals 0. So I set y equal to 0. Don't forget that part, because then you'll have 0 equals, and then you can factor it. What if you can't factor it? This is a big follow-up. If you can factor it, you should. If you can't factor it, quadratic formula. All right, so this one can factor, so it would just be x plus 1 and x plus 4. And then I got my answers. X plus 1 has to equal 0, and x plus 4 has to equal 0. Solve my 2 little equations. If it wouldn't have factored, though, I'd be sitting here still if this was like a 9. Then what do? Then you put it in the quadratic formula. X equals negative b plus or minus square root b squared minus 4 is over 2. All right. All right, so there's the help that I can give you on that topic. Any other questions off the purple packet that didn't have stumped you? Yes, sir.
Number
3 dogfish. Okay. So the general topic is for the graphs shown, I should say the specific question here is for the graph shown, sketch on different set of axes, include all corresponding points, etc. So basically what it's saying is these are being transformed. They're being changed, right? Okay, let's go through the basic transformations first, and then I'll get to the one you specifically asked about. What if I had f of x plus 4 minus 7? You take the function and you move it where? 4 to the left, and then down 7. Okay, how about now? What's that negative in front do? This reminds me of high-low. Horizontals on the inside, verticals on the outside. These are vertical changes out here. That's a vertical reflect, so it's over which axis then? Vertical's up and down, so it's going over the what axis? It's going over the x. Good. All right, so that's a reflection over the x. And what if I put a stretch in here, like an 8? Now I should really put a parenthesis around that too. And that's going to make it get 8 times wider, true, false? Horizontally bigger by 8, true or false? False, because you don't trust the stuff on the inside. That actually makes it horizontally narrower, 8 times narrower. So if my graph used to look like this, I'll make it really simple, a big wide V. If I make it horizontally narrower, it would squeeze it down. It seems like it's horizontally wider, 8 times wider, but it's not. It's 1/8 as wide. It always does the opposite of what you would think. All right, now how about the whole 1 over x thing? Oh, any questions first? Okay, so what if you put 1 over a function? Do you remember doing that? First thought for me is there's going to be at one point there's going to be a problem. What causes a problem when you put 1 over a function? Yeah, if the function was ever 0, then you'd have a problem, right? So let's say I had a graph and it looked like this. Yours doesn't look like this. I'm doing this differently on purpose. What if I put 1 over that function? Well, the first thing I'd do is find this spot, and I'd say at that spot, my new function can't exist. So what do I do there? Asymptote. Remember this thing? What were the other spots that were important when you did the 1 over thing? Yeah, when f of x was equal to 1, do you get that special? Because it'll be 1 over 1, which is 1 again. It'll be the same as it was. So let's say that my graph hits 1 here and here. Then in those 2 spots, my new graph will be exactly the same. And then let's say it hits -1 right here. I'm going to cheat and just make this a little easier for you. Extend that out to, that's where it hits -1 right there. Then those are the only 3 spots that the old function and the new function will be exactly the same. Then do you remember this way to do this? You say, if this is getting really small, we're putting 1 over really small, which makes it big. So if this gets closer to 0, this, the new function, is going to get bigger and bigger and bigger. Okay? And this, as it gets bigger, 1 over big gets smaller. So kind of shaping up now. Gets closer and closer to an asymptote. And then this one does do something weird. Let's say that this is 1/8 right here. Do you get at some point it'll be 1 over 1/8, which would be 8. And therefore it would flatten out right there. That's how you do an inverse of a graph. All right. If I were you, I'd try to get this done tonight, and then you'll be left with only, oh, I got these 6 I still don't know how to do. That'll help you narrow down your problems. I know you might not be able to finish, but try. That's all I got for you for today.